Hi everyone. So today we're going to continue talk about Sobolev space. So let's begin with some definition first, okay? So we have Sobolev space. So let's consider the general case. That means omega is in Rn, is a domain, okay? So the Sobolev space WKP omega. So this is defined to be all the function, or the f in LP, and so that the weak roots, so they exist, weak derivative d alpha f is also in LP. Okay, and also, so this for every alpha, which is less than or equal to k. So this is the formal definition. And we also know that there's a approximation result, and we mentioned before, even though we couldn't give a proof. So the approximation result is saying that if you take the C infinite omega, so this is a very smooth function, space of very smooth function, right? Okay, and suppose then you suppose you make an intersection. You make an intersection with the WKP. So what does it mean is that you look at WKP space and you identify all those functions which is actually in C infinite, and this function turns out to be dense. So this function to be dense in WKP. Turns out to be dense, so it's dense. So this means that if you have the any WKP function, and such a function can always be approximated by C infinite function. Okay, so this is the result. So another way to look at this denseness is saying that if you take a bar. Okay, if you take a bar of that, that means you take closure. And the closure is done through this norm, Kp. Okay, so if you take the closure of that subspace, then this will become just a WKP. Now this is a very important result because we can, so instead of in order to handle the WKP function, which a lot of functions are weakly differentiable, and you can actually first you handle the C infinite function. That's sufficient, because afterwards you can take the limit in the KP KP norm sense. Okay, and today we're going to see such example later. Now, however, you can see that you have to pay attention that if you just think about this space without intersection with that, and this is not so this is not going to be in that, so this is not going to be exactly the WKP. Why? The reason, even though this function in the C infinite space, the function there are sufficiently smooth, carry infinite order of derivative, but however, you can see that the boundary, near the boundary, this kind of C infinite function may go up. So therefore, the function in C infinite may not be in the not even in the LP space. So therefore, not to mention about derivative. So normally this space itself is not going to be inside that. Okay. So you have, I see a few examples like this. So let's say this is AB. So you just think about one dimensional case, okay? The function. So let's say the function like this is a C infinite function, but however, near the B, the function may go to the infinite, so that the total area is not bounded. So therefore, this space, this function is not going to be in L1, for example. And you can create a function, such a function which is not in LP. So such a C infinite function is not going to be in the Sobolev space. Okay, but however, there is kind of things if if you consider a special case of C infinite function, and this function will always be in Kp. So that's the C infinite plus small zero here. Now what does it mean? So this is all the so that the support, the closure, you see how we just hold on one second, okay? So, like in the one-dimensional case, so this space that means the function has to be near zero. Near the boundary, the function becomes zero. So it's like this. So here's the boundary point. We have two boundary points in the 1D case. The function made like this, and it becomes zero here. Okay. So there's no boundary issue for this kind of functions. Okay. They always, so this kind of function is smooth, but also it has to be always in the LP, including its derivatives, because everything will become zero near the boundary. Okay. So you can see so therefore C0 infinite. Okay. Okay. So this one is in the WKP omega. Obviously, so this one will be here. Okay. Now here, so therefore you can see this is a smooth function, and this is the weak function, a weak derivative. So therefore I can take the closure of that, and the closure also you take under the Kp norm. So you take a closure, then you can see that you get a closed space in WKP, right? It's a closed space. So this closed space, so C0 infinite omega, this closed space is also itself will become a Banach space. It's also complete. But however, the question is whether this one, if you take closure of that, do we have something like this which equal WKP? The answer is no. So this one is only included in WKP. This means that this space here is a subspace. It's not going to be the entire space. It's a subspace, because the reason is very simple, because in the boundary of this kind of function, so they are all equal zero. So if you take closure, somehow in some sense the weak solution will still, the weak function will still carry its boundary zero conditions. Okay, so therefore this is not going to be in the entire space, and we're going to give a name for this subspace. Okay, this is just a subspace. So this C0 infinite omega bar is defined to be W0 Kp omega. Okay, so that's a new concept here. So this is going to be the main thing we're going to talk about today. So W0 Kp is a subspace of WKP. Okay. Now W0 Kp carries lots of additional property because of the zero there. So today we are going to see one of them. It's called a Banach inequality. Okay. So let's begin to move this. Okay. So so here the thing we're going to talk about is a Banach inequality. Now, what does inequality mean? So this inequality is applied to functions and in the W0 Kp omega. Okay. So what is inequality say? This inequality says, so let's consider a simple case, the case that k equal 1. Okay, just consider k equal 1. Okay. So first, let's before I introduce this inequality, so let's look at the norm. Okay. So W, so take F in this space, then the norm of this F, 1P equals 1. So from the definition of solid state, we know that this is going to be equals to the F P, right? Fp, then what? You add this another term and sigma, then you have all the derivatives. So let's say dj f p, okay, and j. So this is one n-dimensional case, j equal 1 to n. So for the W1P space, so norm, 1P norm can be written like this. So not only including the F, LP norm of F, but also including the all the first derivative term. Now this norm somehow can be written, so it means equivalent. So we can written in an equivalent form. It's just equals to F, the P plus the gradient of F of P. Okay, now the why this only says it's equivalent, it's not going to be equal, because if you take the gradient, you take all the derivatives, square it, they take a square root, right? So therefore this sense is in this sense they are not always equal, but however they're equivalent. You can bound it from below and above. So therefore sometimes we are using this as the W1P norm. It's simpler because you don't have to use sigma, just the gradient F is sufficient here. Okay. Now with this introduction, then you can talk about the inequalities. Now what is a Penrose inequality? So this inequality simply say that, now we'll talk about this inequality now. So this inequality simply then say that if you take the F, the LP, okay, so this piece norm can be controlled by a constant. Okay, a constant times the gradient of F and piece norm. Okay, so what does it mean is now here what is a constant? And this constant C is depends on it depends on omega, and also depends on n, something like this. Okay, and we're going to see later how this constant is depends on omega. Okay, now so this means that you can see this is actually the first term of the norm, right? And this one is the second term of the norm. So what this means is that this norm actually can be controlled by that. Can be controlled by this. Okay, the gradient of F piece norm. Now this is a very significant result. So now you can see that because of these things, you can see that this one you can continue. Is equivalent. Okay, it's equivalent just by the gradient of F of P, because the first term, the piece norm of F is can be controlled by that. Okay, and so therefore this norm is not equivalent to that single term. That's sufficient. That's the main result of the Penrose inequality. Okay, and it's equivalent by this one is because the F1P norm can be controlled just by the gradient of F, because this one is also right, this, and this things obviously is controlled by the omega norm, so they're equivalent. Okay, so today we're going to give a proof of this result. Okay, so that's the main purpose. So so the proof is we're going to show that the piece norm, that the F piece norm is controlled by its derivative. Now all this proof, we can have this result. The main reason is because we have a zero here. We have zero. This is we're talking about W01P space. We have this result. Now without the zero, then this is not true. This is not going to be true. For instance, if without zero, you can take F is constant. If f is constant, then here this is a, so like constant 1, so this is non-zero. But the gradient of constant equals 0. So 0 cannot be controlled constant. So obviously it's not really sure. So, but however, when you have a 0 here, then you have this result. Okay. So in order to see the proof of this, so let's consider the one-dimensional case first. Okay, it's easier. Consider one-dimensional case is easier. So let's consider this case. So let's consider f in W1P AB. Okay, W1P AB. Okay, and also of course it is 0 here. Okay. Now here we have to this is the example in which we want to first to prove something using the C-infinity function later first, and then you pass by limit to the general case. So even though you can see I pick up a function in W01P, but let's assume first. So let's first assume that the f is actually in the C0 infinite AB. Okay, so I'm going to prove this one for the smooth function first, and then by the completeness I can density I can pass to the general function using limit process. Okay, so let's look at this case first. Now if f is in C0 infinite, so obviously you can see that the fx, okay, can be written by the fundamental theorem of calculus. It's a one-dimensional case, right? It can be written as a x then f prime s ds, right? That's the fundamental theorem of calculus. So if you integrate it, you get fx minus fa. But I know that fa equals 0, and also fb is also equal to 0. So it's just using this, you can see that you can get these expressions. Okay, so that's our starting point. So from this expression, so I can begin to then I can do some estimate. Okay, so I'm going to take a norm. I'll take absolute value of this. So this means that you can take fx. Okay, and then you can see that this is less or equal than integration ax then f prime x and yes, so this s. Okay, so this is the standard estimate, very simple one. And then you can see that this can be controlled by just AB. So replace x by b is bigger than f prime. Now you can return to the x. And yes, you'll get that. Okay? And therefore, so you can see that you can use the Holder inequality here. So I will think about this is 1 times the f prime. Okay? So you using Holder inequality here. Okay, so this is going to be less than AB 1 times something. And so I'm going to look at the second integration first. It's just AB f prime p dx, then here is 1 over p, right? So 1 over p plus 1 over q equals 1. So you can determine the power on the first integration. The power is, so 1 over q should equal 1 minus 1 over p. So this is equals to p minus 1 divided by p. Okay? So you can see that the power, but no matter which power you put on 1, you're still getting the 1. So it doesn't matter. So this is the integration. The outside power what is outside power? So this is q. Okay. Outside power is 1 over q, right? The 1 over q equals p minus 1 divided by p. So the outside power is needed because you have eventually the integration will become b minus a. So this one is become 1. So this integration is just equal b minus a, then p minus 1 over p. Okay, that's it. So therefore, here, so this one is just the norm of f. You can consider this a constant. The p's norm. The derivative here. Okay, so I have this estimate, right? And then I look at the the fx to the p's power. So this power, if you take the power on both sides, so this one will be less or equal than b minus a. Then power to this one will become p minus 1. Okay, and then you have f. There. So you can see the right side appears to be a constant, and this to be a constant controlling the entire function, the fp's power. Okay, and then you do the integration from AB, and here integration AB. Okay, so because this is a constant, so integration is means that this is just equal this constant b minus a, p minus 1, then times f prime p. Then times what? Then times the length of this interval, right? So just another b minus a. Okay, so this is another b minus a, so will be cancelled, can combine with this. So it's cancelled with the 1 here. So you get that sensitivity, okay? And then you take the p's norm, the LP's norm, the power, LP's power, okay? You take the LP's power on both sides here, so therefore the left side will become the fp norm should be less or equal than, then take the p's power here, 1 over p's power, you will get the b minus a here, then times, sorry, I forgot to put power here. Okay, then you take the 1 over p's power, you will get it back to the f prime p. Okay, now you see I get this cup. I'm getting this a nice inequality. Okay, so this one, this is the c, the constant c. You can see in this case only depends on the length of the interval b minus a. So it does depends on the on omega, right? Okay, so this is the result. Okay, but however you can see that in this proof I have assumed that f is in C0 infinite AB. Okay, and now we are going to use the limiting process to pass to the weak function. Okay, to the function with weak derivative. Okay, and this can be done in a very standard procedure. Okay, so now suppose that you have f in W 0, 1p AB. Okay. Suppose you have such a function, and then you choose, because C0 infinite is dense in the space, so you can choose a sequence fk, okay, in C0 infinite AB. Okay, and this is a fk, the smooth function, so that fk converge to f in the the W1p's norm. Okay, so for each, so because the fk is smooth function, so I'm going to have this result, right? So if I put k here, so this can be true. Okay, and this constant is independent on k because it's only just b minus a. It's fixed. So now you can let the k goes to infinity. If you let k goes to infinite, so fk is going to f, obviously in LP, and also the fk derivative also goes to what? The weak derivative of f prime, because this is converging to f in the LP norm at the the W1p norm. So letting this, you immediately get this ft less or equal to b minus a to fk. No. And the reason you can get this conversion is because in this process, letting k goes to infinite, this guy converges into this, and this guy converges into this. So you will keep the order in one. So that's a proof in the one-dimensional case. It's very simple. So this is a proof. It's important. So you have to understand the argument of this proof. Okay, and these are required in the final. Okay. And here, so this is a one-dimensional case. Now we're going to look at the higher dimensional case. It's basically the same proof, but the slightly changing the argument. Okay, but for the simplicity, I was just thinking about the two-dimensional case, and this two-dimensional case is also required in the final. So you have to be careful. Okay. So in the two-dimensional case, so let's look at something here, the domain. So in the two-dimensional case, so I'm going to look at the coordinates. So the domain is maybe like this. So let's assume that you have a bounded domain. Okay. So bounded domain, you can assume that the domain is restricted between these two vertical lines. So AB is like this. Okay, it's like this. So this is our omega. So this is x1 and x2. Okay. So we have a function. Okay. The f is in the w1p and 0 and omega and this omega. So as we did in the one-dimensional case, may assume that the f is actually in the C0 infinite omega. Okay, so look at this case first. Okay, and so with the assumption that this omega is bounded like this. Okay, and now because it's a smooth function, so you can perform the same argument as we did previously. So what we're going to do is you take only one variable. You work on only one variable. So like this, you take f, x1. So this function can two variable, right? So you look at this x1 variable only. So in this analysis, I keep the x2 fixed. So once you keep x2 fixed, so you can see this is just a one-dimensional function. So this function can be written as, again, using the fundamental theorem of calculus, is written, you can see from a and to x1. Then you have the f, s. Now you're using partial derivative here. So you can use the df, dx1, then s, and x2. So you integrate the first partial derivative, okay, from a to 0. Now here, because the function is in the C0 infinite omega, so this means that the function will become 0 nearby the boundary. So therefore, I can certainly assume that the function here, I can extend this function so that they all become 0 outside. Then the function, you can think about this function is not only defined in omega, but also defined on the strip, the entire strip. And the strip can be goes from to the minus infinity, right? So the function is also defined to 0 here. So this is just for simplicity in the expression, okay? All right, so because of this result, you can see that I can, again, estimate these things, okay? And you can put absolute value sign inside, all right? And also, then you can remove x1 to b. So you will have this standard basic estimate. And then the next, I'm going to use the Holder inequality. Holder here, as we did in the one case. The Holder case, actually we did previously, the components, I mean the Q and the P relationship. So therefore you can see that the first one is integration, again it's integration from A to B with function is 1, right? So therefore the first one will again reduce to B minus A. is b minus a. And to what power? Now, if you still remember, p minus 1 to the p. Okay? And the second one is the p's power for the partial derivative. So you can see this up. Okay, so I have to, instead of writing this up as the norm, I have to use, again, the integration a to b. Okay? So there will be the df dx1, the partial derivative, p power, and dx, then 1 over p. So I'm going to get this, okay? So basically this is follow from the same argument, is a 1D formula. Because here I'm fixing the x2, okay, fixing the x2. And now you take the power, you put power back. So f x1, x2, okay? So this is the p's power. Now this one will be less or equal than what? Less or equal than b minus a, okay? So then take the p's power, so you have become p minus 1 here. And then you have, so I'm not going to write this, it's a norm. So that's the main difference between the 1D case and high dimension case. I have to keep the integration here. So once you take the p's power, so you're removing 1 over p outside. So you have this integration, a to b. Then df1, no, df, dx1 to the p's power dx, sorry, to write dx1. 1. Okay, so this is what we have right now. Now this is key inequality, okay? And then I have to do the double integration on both sides, right? So this will become like this. So this double integration. So I'm going to now focusing on the 2D case. I'm going to separate the integration as iterated integration. So therefore, I'll use a double integration sign. So this one f x1 x2 p power dx1 dx2. Okay, on the right side, on the left side. So this one will be equal to. So again, I use double integration on the right side, and then so this one is a constant. So I move this constant outside, but I'm not going to remove this. This is not going to be constant. Why this is not going to be constant? Because you can see this f depends on x1, x2. So x1 disappear because of the integration, but x2 is still there. So when you do double integration, this is not going to be a constant here. But first one is a constant, I can move out. So b minus a, p minus 1, okay, as usual. So then I'm going to write this clearly. So this is a double integration. But when I write this double integration, I have to be written this in this way. So I put it dx1 first, okay? Then you have the integration, and from minus infinity to plus infinity. So I'll treat this one. So this is in omega, right? But I know that I extended function and to be 0 in the strip. So therefore, I can think about this omega now become the interval AB cross the minus infinity to the plus infinity. Okay? So therefore, that's why I can write this way. And then you can have the integration AB df dx1 and p dx1. So this dx1 is here. It's because of this. I have to make a connection here. So this dx1 goes to this dx1. Okay, so these are the same integration variable. Okay, and then you have the dx1, new dx1 here. You have another dx1 with the minus infinity to the plus infinity. So I'll combine with this one. So you can see that in the multi-dimensional case, you have a iterated integration, and you can always, because we're dealing with smooth function, so you can always exchange in order of this iterated integration. Okay. Now I'm going to write these things like that. So what does it mean is I combine. So this is original one-dimensional integration. I combine another piece of the iterated integration is 2. So I think about these things, okay, together. And this dx1 is after this 2 iterative integration. So you can see that if I combine these two things, and this things is just give you what? It's just give you the df dx1, the piece power, then you the double integration of omega dx1 dx2, right? That's it. Okay. So that's the return to and this one you can see that since after the integration of this, so this become a constant. No longer depends on x1 and x2. So therefore this one, this integration will just become b minus 1. Or b minus a. Okay, then times this, b minus another b minus a here, p minus 1. So these two cancel with minus 1. Okay. Now if you think about this way, then you take the power 1 over p outside on both sides. Then you will get the final inequality. The final inequality is just it's just like this. F and the piece power. Okay, and it's less or equal than b minus a times df dx1 and times the piece power. That's it. And this one obviously is less or equal than b minus a, the gradient. So gradient is greater than this, right? Gradient F. So that you can see that in the for any function in the C0 infinite, I established this result. And this constant, the constant here. So this is our constant here. Constant. So in this case, the constant is very simple. Okay. So finally, so you can using the limiting process. So using the limiting process, so letting fk and in C0 infinite, so fk converge into f in the w0kp. Okay, so use this limiting process and letting k goes to infinite, and so this is going to be true for k, right? So then you let the k goes to infinite, so you can see that you can establish this same equality for any function in wk for this weak function. So that's a proof for the two-dimensional case. Now if you get the higher dimensional case, basically it's follow the same line of the proof. Now this proof gives us some additional constants. You can see that in this proof, and actually this constant c depends on what? Constant c depends on b minus a. Okay, so this means as long as the width of this domain is bounded, the width of this domain is bounded by b minus by a finite interval, something like this, and then you're going to get this. So this means that even if the omega itself is unbounded, but however, suppose this domain is the width of this domain is bounded in one direction, then you will have this Pondeles equality. Okay, so this equality is not necessarily be true on just the bounded domain. It can be also true for the unbounded domain as long as the width in certain direction is bounded. Okay, so there's lots of consequences of this result, and we may want to look at later if we have time. Okay, so this is the main thing we're going to talk about today. Okay, and we're going to have further discussion tomorrow later and during the Zoom meeting. All right, so we're going to close today.